Section 9. I kind of hinted at this already, but polar bonds can lead to polar molecules. But it turns out they can also lead to nonpolar molecules, which we'll see here in this section. Nonpolar bonds, it turns out, always lead to nonpolar molecules. There's no other way around that. But that then has an effect on how they interact with one another, something called intermolecular forces. And so I really feel like this should be two separate sections, but the textbook covers them here together. If the video gets long enough, I may split it into two, but we're just going to go ahead and dive into this section now. So it turns out that when you have nonpolar covalent bonds, you are automatically a nonpolar molecule. That's the easy one. It turns out, however, though, if you have polar bonds, but they are in a tug-of-war against one another, then you can end up with your dipoles canceling out. And then because they cancel out, you end up with a nonpolar molecule. So it turns out that carbon dioxide, this bond here between the carbon and the oxygen is polar. The bond between the carbon and this oxygen is polar. It's the same math, it's just two different atoms, so we kind of have to describe each of them. Well, if we do that dipole notation that we talked about with the arrow on there, you'll notice that we don't end up with a dipole here, that we end up with a negative side here and a negative side there. Well, that's not a dipole. Those poles have the same thing. And because of that, the dipoles cancel out. And this happens anytime there is a symmetrical arrangement on polar bonds. And so polar bonds that are symmetrical are going to end up being a nonpolar molecule. And so here, on this one, it's a little bit hard to see in the three-dimensional model here, but with the chlorines here, they are all pulling the electrons towards themselves. They're all the delta minuses. The carbon here is the delta positive. Well, then the whole outside ends up being negatively charged. Or again, the way you can think of this is that the tug of war, no one wins. And because of that, then even though we have a polar bond in there, and we actually have 4 polar covalent bonds in there, the molecule is nonpolar. You get polar molecules anytime they are not symmetrical. And so if you have polar bonds and asymmetrical, then you get a polar molecule. And so hydrogen chloride is polar because the opposite sides end up having opposite charges. Water. This is important for water. Water ends up being polar. The oxygen is a delta minus on both these. The hydrogens are these delta pluses. And you end up with the pole here going towards the oxygen. But because it has that bent shape, the 109 degree angle in there, because it has those electrons around it out here, it means that this tug of war doesn't cancel out, but there's a pull kind of up and to the left, a pull up and to the right, and the left and right components cancel out, but the up and down parts don't, and we end up with a positive side and a negative side of the molecule. It's literally a positive side down here with the hydrogens and the negative side up here with the oxygen for the molecule. And so we have a polar molecule. In fact, if water happened to be linear, it's not possible for it to be linear, but if water happened to be linear, well, the fact that would make it nonpolar. You would end up with this and this, and it would be nonpolar. And it turns out the intermolecular forces are such that it would actually make life on Earth impossible. If you have me live, I'll elaborate more on that, but I'm not going to suck up time here in the notes where it's not necessary. But it is essential to life that water is a polar molecule, and then has a huge effect on how water behaves. So anyway, again, if it's asymmetrical, then you can end up being polar. Ammonia is polar because, again, it's asymmetrical and we have polar bonds. If we go back to the chart that we had in the prior section, the things that have 0 lone pairs are going to be nonpolar. molecules. The things that are not are going to be polar molecules. So, getting into an example here, OF2. Well, I'm going to cheat here because we did this one in the last section, and I'm just going to jump straight to what the answer is. It's like that. Well, if the answer ends up being like that, then we have oxygen. It has 4 bonding regions. Those bonding regions are broken down into 2 things bonded to it and 2 unshared pairs of electrons, which gives us a bent shape and a 109-degree angle. And then because of that, we are going to end up polar. If we do the delta signs here, the fluorine is the most electronegative element it is, so it's got to be the delta minus. There's the delta plus. You could figure that out by looking at this up here as well and finding out that it is polar. But then what there's going to be is there's going to be a pole this way, and there's going to be a pole this way, and together that's going to result in a polar molecule. And so, yes, it's polar. For this question, we're going to need to draw out the dot models. I hope at this point you've had enough practice with the dot models, but whether you have or haven't, I'm going to encourage you to pause it here. I'm going to not make this video take longer because we've already done several examples like these already, and so I'm going to just quickly do the dot models here on my own, cut that part of the video out here real quick, and then we'll come back and just answer the question about the shape and is the molecule polar or not. So, check your answers. Hopefully you're correct, but these are the models for each. I went ahead and looked up the electronegativity values as well and jotted those down here, mostly because I want to make sure that they weren't trying to sneak in a nonpolar covalent bond. Because if any of these were nonpolar covalent bonds, then automatically they'd be nonpolar molecules. But if you look at the electronegativity differences of 0.7, 0.7, and 1.5, all of these are going to be polar bonds. And then the question becomes, are they polar molecules? So this one here, there's 4 bonding regions, which is broken into 3 things bonded to it and 1 unshared pair of electrons. Well, that's going to put us right here at the trigonal pyramidal shape, and because of that, it is going to end up being polar. When we're done going through all these, I'll draw the dipole moments on there, the arrow notation on there. Anyway, this one here, we've got 4 bonding regions around it, but only 1 thing bonded to it and 3 unshared pair of electrons. You actually notice that that's not on this list. That would be 1 bonded atom and 3 unshared pair of electrons. Then it's going to end up being linear. And it should be obvious that it's linear because it's only 2 things. It has to be linear. Well, it turns out that if it's linear and it's asymmetrical, which this one is, then yes, it's going to be polar. The last one over here, we have 4 bonding regions broken up into 4 things bonded to it and 0 unshared pair of electrons. And so then that gets us into this region here where it is tetrahedral bond angle of 109. And this one turns out to be a no because of those 0 unshared pairs of electrons. So getting into drawing Y on each of those, here you end up with the poles going out this way, but it makes the phosphorus be a positive side and the bromines all be negative, and then because it is actually trigonal pyramidal, those bromines are all down there on the bottom with the phosphorus sticking up above them, and so then it does end up having a dipole moment is what we call that. This one here, the bromine's more electronegative. That one's easy because it's just your 1 positive and your 1 minus there. Here, all the positives end up at the center and all the negatives end up on the outside edge. And so then because of that, even though there's this these poles, those tug of war end up canceling one another out. And so even though all of these are polar covalent bonds, only 2 of them are, yes, polar molecules. And one of them is no for being a polar molecule.